mentioned before the break, our simplistic model for the dynamics of the Brownian particle has certain limitations. It seems to be unphysical because the square of the velocity tends to blow up with passage of time. The source of the flaw, and we found that one of the reasons could be that there is an asymmetry as far as the number of collisions are concerned when a body is in motion in a uniform fluid, and that arises due to the fact that the number of particles hitting the Brownian number of molecules hitting the Brownian particle from the front as it moves forward tend to be more than the number of particles hitting the particle from behind. And this creates, because the particles hitting it from the front are going to decelerate the motion of the Brownian particle, therefore, it amounts to a kind of damping, and in general we model that damping as a linear term in velocity. So, our Langevin equation with this damping term gets modified, and we have the new Langevin equation that is given in the red box here. V dot is equal to minus gamma v plus L t. We shall be exploring more about L t, and that will be the subject matter of most of our discussion, but for the moment gamma is a constant, a damping constant, in the sense that would relate to the viscosity of the fluid in which the Brownian particle is submerged. Right. Now, the properties of this random force represented by L t. Now, the first thing is the axioms that we may assume, that we profess before we write the statistical properties of L t are similar to what we did earlier. The collision is all the collisions are practically instantaneous, successive collisions are unrelated, uncorrelated, and the collision force varies rapidly. And therefore, keeping that in mind, we can write the autocorrelation function as L t dash is equal to capital gamma delta t minus t dash. What capital gamma represents? Well, capital gamma represents the magnitude of the force by which the molecules collide against the Brownian particle. In actual fact, to have been more precise, the collision impact of collision lasts for a small period of time t minus t dash, and therefore, we should have introduced a function t minus t dash, because t minus t dash is very small compared to the other scales of time that are relevant in the present problem. We assume that t minus t dash is instantaneous, and we make use of the delta function in representing the autocorrelation function between L t and L t dash. Therefore, the random force L t is a stochastic, it is a random, therefore, and it is a collection of random variables, it is a sequence of random variables, therefore, it is a stochastic process, and it incorporates the impact of the background noise of the collisions of the various molecules against the Brownian particle. And these are the two fundamental properties that we come to. The average of L t across all realizations will be 0 in an ensemble, and the autocorrelation, as I mentioned, is given by capital gamma delta t minus t dash. Now, the Langevin equation which we saw just now, V dot is equal to minus gamma V plus L t is an example of a stochastic differential equation. A stochastic differential equation is a differential equation where the coefficients of the various variables are random variables in themselves, and they are also functions of time. In other words, you can write a stochastic differential equation in the form of dx is equal to a x t dt plus b x t d w t. These are the two variables and A and B are functions of x and t. So, this is a stochastic differential equation. The coefficients of the variables are random functions of time with given stochastic properties, and the variables themselves, one or more may be stochastic in nature, may be Brownian motion, may be the infinitesimal Brownian increment. Now, we look at the solution of the Langevin equation. The generalized Langevin equation with the damping term. Let us assume for the moment, let us start with the situation where there is no force, the LT is equal to 0. The solution is easily written in that case. We have Vt is equal to V0 exponential minus gamma t. This is the solution, straightforward solution when we have no damping, no random force, no external force, isolated particle subjected to only a damping force. Obviously, the damping force will tend to act on the particle in such a way that over passage of time and the particle velocity will diminish to 0. Now, before I proceed further, I had assumed that the average of LT is equal to 0 and the correlations, autocorrelation functions of LT are delta correlated in some sense, although with some scaling. Now, what happens if the average of, why is it that we can assume the average of LT as 0? The situation is that even in the case where the average of LT is not 0, the residual average can be combined with the drift term, that is the gamma v term, and we can thereby retain only a term on only LT which has a mean of 0. Let me explain again. Suppose we find that the average of LT is not equal to 0, then whatever that average is, that average value of LT can be added on algebraically to the gamma term, and whatever remains will obviously have an average of 0, and that can be treated as LT. The autocorrelation functions will obviously not change, because if the even if the autocorrelation functions have a non-zero mean, we can measure the autocorrelation functions in terms of deviations. So, that is not a major issue. And as I mentioned earlier, gamma is a measure of the strength of the damping of the driving force of the stochastic force. Right. Now, why do we assume that there is no correlation between the autocorrelation is a delta correlation? That is very important. There are two reasons for this. Number one is that the time scale over which the force acts is very small, and because it is very small, it acts like an impulse, and impulse which is limited to a particular point in time, and therefore, we use the delta function in time to model this. The second thing is that the frequency of correlations is very large, as a result of which because the Brownian particle gets hit by molecules so rapidly that it loses memory of what had happened earlier, or the impact of any earlier correlation is dissipated very rapidly because of immediately following correlations. So, these two factors combining together result in delta function correlation being an appropriate usage for the stochastic force that forms the applied force in the Langevin model. And of course, these are the two moments, the mean and the variance we can use for describing this particular force LT, the two moments that are required for describing the force, because we assume it to be Gaussian. Now, there are certain technical issues which in this particular course is not really relevant, but the important thing is that the Langevin equation may not have a unique solution for a given initial condition. However, it does have a local solution. Now, the important thing is this local solution may or may not be unique. So, what do we have? There may be a global solution, there may be a local or there may not be a global solution, but it is likely to have a it is going to have a local solution. That local solution may or may not be unique. So, let us now look at how we move further towards that solution. Right. So, now we have first of all let us arrive at the solution here. We have V t is equal to V 0 exponential minus gamma t in the situation when the driving force is absent. Only the damping force is there, then V t is equal to V 0 exponential minus gamma t. There is the velocity gradually dies down. Now, therefore, the solution of this expression V dot t I am sorry, V dot is equal to minus gamma v plus L t will be V t is equal to V 0 exponential minus gamma t plus integral d s L s exponential minus gamma t minus s. Let us see how we arrive at the solution to start with. Now, this is a first order inhomogeneous differential equation. The Langevin equation that is given to us is a first order inhomogeneous differential equation of the form dy by dt plus a t y is equal to f t. So, it can be solved simply by using the integrating factor approach. We work out the integrating factor. The integrating factor works out to exponential gamma t. We multiply both sides of the equation by exponential gamma t. When we multiply both sides by exponential gamma t, we find that the left hand side turns out to be a complete derivative of v exponential gamma t, and therefore, the solution that we get is v is equal to exponential minus gamma t. Now, this exponential gamma t on the going on the right hand side will give you exponential minus gamma t, and the integral has to operate over the function on the right hand side, which is 0 to t ds. S is the integration variable, ds L s exponential gamma s plus c. C is a constant. Now, how do we determine c? We determine c by the fact that when the force is absent, our solution is what? Our solution is given, our solution is this expression V t is equal to V 0 exponential minus gamma t. So, this enables us to find out the value of c, because when L t is equal to 0, our solution must turn out to be this expression, and it follows that the complete solution is now exponential V t is equal to V 0 exponential minus gamma t integral this expression exponential minus this thing, and this should be plus here, plus integral ds Ls exponential minus gamma t minus s. This should be the complete solution of the Langevin equation. Now, let us investigate if the relationship between this force L t and the concept of Brownian motion. As I had mentioned earlier, this Brownian motion is the cornerstone of all stochastic processes, and that being the case, it makes its presence felt almost everywhere and anywhere whenever we have stochastic analysis to do. So, let us find out what L t has to do with Brownian motion. For that purpose, we set d of u t equal to L t dt. Putting this making this substitution, we can write the Langevin equation as dV t is equal to minus gamma v t dt plus d u t, because L t dt is equal to d of u t. Multiply by an arbitrary non-stochastic continuous function f tau and integrate over between 0 and t, we get the equation, which is equation number 2, integral of 0 to f tau d v tau, that is the left hand side between 0 to t, and the right hand side is this expression. Now, you can see that the integrations become viable. When we do the integration, what do we get? We get v t minus v 0. Suppose we take before that, suppose we take v tau equal to 1, f tau equal to 1, I am sorry. Suppose we take f tau equal to 1 and then do the integration. What do we get? We get integral 0 to t d of v tau, and that becomes v t minus v 0. And on the right hand side, what do I have? Minus gamma 0 to t f tau is equal to 1, recall v tau dt d tau. What is v tau? V tau is the velocity, remember. So, it is dx tau upon d tau into d tau, that is dx tau integrated between limits of 0 to t in terms of tau, and that gives us x t minus x 0. And the last term, when you have f tau equal to 1 and you integrate d u tau between 0 and t, you get u t minus u 0. So, this solution is what we get when we have f tau equal to 1 and we do the integration. U is a function of time, right. U t has a particular value, u 0 has a particular value. Now, we adopt the process of time slicing. We slice the time interval 0 to t into infinitesimal or very small intervals. Let us say we slice them into n time intervals, n time non-overlapping intervals, non-overlapping partitions, and we write them as 0 t0 to t1, t1 to t2, t2 to t3, and so on up to tn. So, naturally t0 will be equal to 0, tn will be equal to t, and the various points along the interval will be, this will be, say this is 0, this is taken as t0, this is tn, and this is taken as t, and you have different points along this representing the partitions of the timeline. Partitions of the timeline, and you take the values of the function u t at various points along this timeline and form this particular sequence u k t k minus u t k minus 1 plus it says u 0 u 1 u t 1 minus u 0 u t 1 minus u 0, and then you have u t 2 minus u t 1 and so on. You form this particular expression. Obviously, the sum of these expressions, if you do it, all the intermediate terms will cancel out and you will get the left hand side here. Now, we postulate that u t is continuous, it is a Markov process and it has 0 mean. Let us see what is the justification of these three things. Now, we have dut, by definition dut is equal to Lt dt, therefore, ut is equal to, when you integrate both sides, you have ut is equal to u 0 plus integral 0 to t L tau d tau. Now, this integral has to be a continuous function of the upper limit, and therefore, we find that L t is a continuous function, and therefore, u t also has to be a continuous function. Now, Markov property I had alluded to a little bit earlier. Markov property arises because of frequency of collisions. The number of collisions of the Brownian particle with the molecules is very, very large, something of the order of 10 to the power 10 to 10 to the power 12 collisions per unit time per second, right. So, what happens is, even if you make t this time slicing, even if you make this time slicing very small, there would still be a number of collisions taking place within a particular time slice. And as a result of which, for example, suppose you pick up the time slice t I minus 1, the number of collisions that take place within this time slice t I minus 1 would be very large, and as a result of which the influence of what had happened earlier is very rapidly wiped out from the memory of the Brownian particle. And therefore, one can say that howsoever small I make T I minus T I minus 1, howsoever small I make this time chunk or time slice, this the whatever happens here would not be dependent on anything beyond T I minus 1, anything before T I minus 1, because the frequency of collisions is so fast that the speed or the rate at which memory is lost by the Brownian particle is very rapid, and therefore, for all practical purposes we can say that whatever happens in this interval is at most dependent upon what happens at T I minus 1 and nothing before that, and that is what is the characteristic of a Markov process. So, we can say that u t is a Markov process, that is u t depends on u t minus 1 and nothing earlier than that. Then we have, because of the randomness of the motion, as we discussed earlier, in fact, if there is some kind of a drift, the drift can be incorporated in the damping term, and the net result is that we can, for all practical purposes, we can assume that the mean of or the average of L t should be approaching 0, should be 0. And if we now select the time origin such that u 0 is equal to 0, we must then have the average of u t k as 0. Whatever the value of t k is, whatever the point at which the time slice is, the average value must be 0, provided you take the origin of u 0, u at t equal to 0 as 0, then because the initial point is 0 and every subsequent interval is has a mean of 0, therefore, we have u t k equal to 0. So, what is the outcome? The outcome is that outcome of all the earlier discussions is very interesting. What do we have? We have u t 1 minus u 0, u t 2 minus u t 1, u t n minus u t n minus 1. All these, remember, these are time slices, and u t 1, u t 2 are basically related to the driving force or the random driving force. And what do we find? The random driving force impacts are independent in each of these time slices. They after a steady state is reached, after a point in time of evolution, these increments are also stationary and they are identically distributed with a mean of 0. So, these three fundamental properties emanate from the behavior of the applied force that we have. The fundamental thing is that it is firstly it acts for a very small period of time, infinitesimal period of time, and secondly there are a huge number of collisions taking place per unit time. So, that being the case, what do we have? We have, because of the central limit theorem, if you apply the central limit theorem to the expression on the right hand side, what do we get? You get that this expression becomes a Gaussian and it has a 0 mean and it meets all the requirements of a standard Brownian motion. So, u t is nothing but the standard Brownian motion. That is what we conclude after this slightly elaborate extended analysis, that u t, what was u t? U t was L t dt. Du t was L t dt. So, it is an integral of L t dt. L t is basically some kind of a noise and L t dt integrated over gives me u t, and that turns out to be Brownian motion. Therefore, making use of this particular property now, I can write the solution to my original Langevin equation as V t is equal to V 0 exponential minus gamma t plus, I can replace this L s d s by d w s, and now this becomes an integral or over infinitesimal Brownian path Brownian motion. V t is equal to V 0 exponential minus gamma t plus integral exponential minus gamma t minus d w s. This is where the infinitesimal increment, Brownian increment makes its appearance due to what? Due to the equivalence between ut and wt. So, just to recap this part of the discussion, the continuity we established, because this integral needs to be continuous in its upper limit, and therefore, ut has to be continuous. So, that was not a major issue. The Markov property arose because the frequency of collisions is so large, being so large that if you take any small interval, even then the number of collisions is so many that the memory carried by the Brownian particle is very short lived, very short lived, and for all practical purposes we can say that what happens in this small interval Ti minus 1 is independent or does not depend on the history of the particle beyond what it was at Ti minus 1. So, that is what is the property of a Markov process. So, therefore, ut was a Markov process because of this. And then we also agreed that because if we assume that we start at the origin, that is u 0 is equal to 0, and because each of these increments has a 0 mean on the average, because if there were any drift, that drift would be captured by the damping term, and we could have a 0 mean process being represented by LT, and that is what was wanted. So, the every increment has a 0 mean, the initial point is 0, and therefore, on the average at any point, you take the average at any point in time, the mean would be 0. So, the mean is 0 here, and so what we have? We have ut minus ut1 minus u0, ut2 minus ut1, all these are independent, of course, they are independent, right, because they represent independent impulses, and on attaining a steady state, these increments also become stationary and they become identically distributed and they have 0 mean. So, all these properties we have established, and because of these properties, if you apply the central limit theorem to this, then you end up with ut being a Gaussian variable, a normal variable with a 0 mean, and therefore, it has all the requirements of a Brownian motion, and I can write ut as wt. Right. Now, we come to some important observations of this model, of the revised model. We have talked about the earlier model, we talked about the flaw in the earlier model, the average of Vt square would tended to get unbounded, and now we look at what happens in the revised situation when we introduce a damping term into the model. Now, when you introduce the damping term into the model, the solution, as we have seen, becomes this equation, which is nothing but equation 1. So, clearly if I take the average, of Vt, the second term again goes away, because the averaging over Lt would be 0. We have already assumed throughout that average of Lt is equal to 0. Average of Lt is equal to 0, we have assumed throughout. So, when we do the averaging of Vt, we find that the first term remains, the second term becomes 0, and the averaging is V0 exponential minus gamma t. It is quite clear that as time passes, V0 this average tends to decrease because of the damping factor, and gradually the velocity will fall. Now, let us look at the average of V square t. When we do the average of V square t, again the cross terms will again vanish for the same reason as I explained earlier. The reason was that the average of Lt is 0, and because the average of Lt is 0, the cross term which has one term in Lt and one term in V0, the Lt average being 0, that cross term vanishes, and we are left with these two terms. The first term is V square 0 exponential minus 2 gamma t, that is, this is deterministic, there is no problem with this. The second term involves a double integral, let us call it dt1 dt2 lt1 lt2 exponential minus gamma t minus t1 exponential minus gamma t minus t2. Remember, this integration has to be done over the limit 0 to t. So, since this is an averaging, the angular brackets can be replaced with angular brackets within the integral, because as I mentioned, integral is a sum, and now the angular brackets between LT1 and LT2 are nothing but the autocorrelation functions, and they are given by gamma delta T1 minus T2. So, we have substituted gamma delta T1 minus T2 here. Now, we perform, let us say we perform the T2 integration, then what we end up with is that all T2s will be replaced by T1. When you replace all T2s by T1, exponential, both the exponential terms become the same, and I get exponential minus 2 gamma t minus T1 integral dt1. Now, if you do this integration, it gives me the expression which is given at the bottom of this slide. Let us call it equation 2. A simple straightforward integration of the exponential in this 2 gamma in the exponential will manifest itself in the denominator as 2 gamma, and the rest, when you put the limits, you get this expression 2 gamma t minus 1. You simplify this a bit further, and what I end up with is gamma upon 2 small gamma plus, remember small gamma is the damping coefficient, and capital gamma is the strength of the applied random force, the stochastic force. So, gamma upon 2 gamma plus v square 0 minus gamma upon 2 gamma exponential minus 2 gamma t. Now, as t tends to infinity, a very interesting thing happens now, and the interesting thing happening is that this term tends to 0. As t tends to infinity, the exponential minus 2 gamma t term tends to 0, and that being the case, this whole expression vanishes, and I get a constant steady state value which is given by capital gamma upon 2 small gamma. Remember, this is for a particle of unit mass, right, for a Brownian particle of unit mass. So, in this case, the problem that we had in the earlier model has been taken care of. We end up with a finite value of the average of v square t, and we also have a finite value of v t and v square t. So, the first and second moments both have finite values, and to that extent this model seems physically viable. Right. So, we will conclude here for today. We will continue in the next class with first discussing the Langevin equation and the Fokker-Planck equation, and then deriving a path integral solution for the Langevin equation. Thank you.